Friday?
Yeah, well,
No.
yeah, maybe not. Maybe. Okay, so when work is done, energy is transferred, right? What else? Okay, so for work to be done in physics, a force must be exerted and there must be some displacement in the direction of the force. Okay? So all this stuff can essentially be summarized with these equations. So this is, let's start here. This is what we call in math, and I don't think, did you guys do any of this stuff in pre-calc? Did you do vector or dot products in pre-calc?
No.
Okay.
Yes, you did.
I just answered no to everything.
But you did dot products? Okay. So a vector dot product, just remember what this is. A vector dot product is if I've got these two vectors, force is a vector and displacement is a vector, right? And I'm using D, that's what the OpenStax book uses, and that's what a lot of books use for displacement. S would maybe even be better, right? But for now, we'll just call it D. So force times displacement, when they're dotted, what that means is you're going to take the product of the magnitudes of the two forces times the cosine of the angle between them. Okay, so we're going to practice this today. So it might look, it might look something like that, right? So the absolute value indicates a magnitude. The magnitude of F times the magnitude of D times cosine theta, which is most easily written like that.
So it's force and direction, those are that.
Force and displacement.
So
Yeah.
that's also.
Right, so probably for us, honestly, a better way to write this might just be like this. We could say work equals F delta S cosine theta. Most textbook, for some reason, they call it FD. Okay. Or we could call it FS cosine theta. Whatever you call it, it's pretty clear what it means. And as we go through the examples, you'll see that. So let's try some examples of some situations that some involve work and some don't involve work, right? So from the OpenStax book, that's, I don't know, this guy, I don't know, what's that guy's, mowing his lawn. Scantily clad mowing his lawn. Anyway, he's pushing a lawnmower. And so tell me now, is work being done as he pushes the lawnmower?
Yes.
It is. It meets the criteria, doesn't it, right? Force is being applied. The force and the displacement at least partially line up, right?
Yes.
And is energy being transferred? Yeah, it is, right? He's pushing on the lawnmower. If the lawnmower, well, I'm not gonna say anything else about that for now. We'll come back to that, to the energy being transferred part. But work is clearly being done there. What about this guy here, Mr. Personality? He's walking sideways while carrying a briefcase.
Is he walking straight?
He's walking straight. What do you think? So it'd be that same thing as me. I've got this 1 kilogram mass right here, and I'm walking along like so. Am I doing work on the mass?
Yes.
How come? I'm moving it. Okay. Somebody said no. How come?
It's moving with you. It's part of you. Are you doing work on yourself when you're moving that too?
Well, sure, but I'm just talking about this object right now. Am I doing work on this object? So in what direction am I applying force to it? If I'm walking at constant speed?
That way.
No, I'm not.
Upward.
Upwards, right? Supporting the weight of this thing, right? As I'm walking along like so.
How are
Moving at constant speed. So its inertia is carrying it once I accelerate it. So we're starting the movie after I'm already walking. Right? Start the movie now. And cut right there as I walk out, right? So I'm applying the force upward. In what direction is the displacement as I walk along the front of the room? Okay. That way, this time, right? Force is this way. So once again, I ask you, am I doing work on this? You're right. How come?
Because the force system is going the same direction.
Okay. There is no displacement along the lines of force, or there's no force along the direction of displacement. Right. Everyone think about it. I think this is more intuitive. if you think about it as there's no displacement along the lines of force. Right? The lines of force are vertical, and my motion, my displacement was completely horizontal. Right? If you look at it in terms of our formula, well, what's the angle between the two vectors? The displacement is 90. What's cosine of 90? 0. Yeah, so there is no work being done there. Okay? It's kind of hard to probably see that right now, why that's the case. We'll come back to that. Okay? What about this last example right here? If we're going to carry, this guy's carrying the suitcase up a flight of stairs now.
Yeah.
He is, right? Then there is work being done, right? Because there's a vertical component to that displacement, and the force is vertical, right? Okay, so that probably is a little confusing, I bet. Why is it, I mean, so there's no work being done, but I'm exerting some force. I mean, if this were a 100-pound dumbbell, walking, even if I'm just carrying this at constant speed at the same height the whole time, you can only do that so long before you get tired and it slips out of your hand, right? So that doesn't seem consistent, does it? If you get tired doing it, then why isn't it work?
Because you're still exerting it first.
Exerting it first?
You can exert the force, but if it's not displacing the object, then you're still gonna be tired. Like if you push against a wall, you're not gonna move it, but you'll still be tired.
Right. Okay. And if I stand here and hold this thing, eventually I'm going to get tired. Right. I have to exert. But that's really this is a real common misconception, and it gets in the way of understanding the concept of work. And it has to do with the way our body works. It really doesn't have to do with what the scientific definition of work is. Our bodies are not designed for just holding something stationary, right? When we want to exert forces in our bodies, we use muscles to do that, right? And when you use muscles, there's intramuscular work going on anytime you flex your muscles, right? The little myelin sheaths are sliding past each other, and so there is some work going on inside the muscles, whether you see it externally or not, okay? So it's not a good metric for, does it make you tired, right? If there were a strong evolutionary advantage to being able to just hold stuff without, for long periods of time, which we never do, but if there were, we would have evolved different, attributes. We would have probably had like little cotter pin skeletons where we could just stick a pin in this and let our muscles relax, and just our skeletal system would just hold this thing in place. Something along those lines, right? And some animals do stuff like that. Give me an example. In Pendleton this evening, if you watch an animal, a certain type of animal resting, you might see it might look pretty bizarre. It doesn't look very restful to us.
Horse.
Like a horse. A horse stands up while it rests. Okay, even more dramatically, certain kinds of birds, like you see like a great blue heron, if it's gonna, when it rests, what do birds do when they rest? It looks really bizarre. A lot of times they'll stand on one leg, right? And they can sleep like that. Well, how come? Why can they do that and we can't? Or birds will rest on a perch, right? Birds can sleep on a perch without falling off. That seems like that would make you tired to have to grab that perch the whole time, right?
Because their feet are locked.
Because their resting position for a bird, the tendons are pre-sprung, and so their natural position is to grip.
So they reverse?
Yeah, so they have to apply force to not lock their hands, right? Their talons.
Yeah.
And so it's different than it is for us, right? If you look at this has been like in a lab, you can take this kind of gruesome. You can take a dead pelican. If you take the skeleton of the dead pelican, or you just take the dead bird, you can actually, if you balance it properly, so you have to apply some splinting and things, but you can set that thing up without doing anything artificial. You can put it in this position and it'll stay that way because the joints bend, so they hyperextend, and they're in equilibrium, stable equilibrium when it's standing there. The only thing, what's that? Yeah. Yeah, and they would fall over because there are some little muscular movements that very, very minor ones that keep them balanced, like if there's wind and stuff. But that's sort of an evolved trait. But they have the ability to stand there and lock their legs so the muscles are doing nothing. So it actually is, for them, it's advantageous. It's energetically, it's an efficient thing to do. And they tuck that leg up. Most of the time, they tuck that leg up so they can conserve heat. So they're not radiating heat through their legs. But it's all about just conserving energy in the wild, right? Not storing fat and conserving energy. And so they have a little bit of different, or anatomically a little bit different. And so for them, it's easier to see that standing there does no work. For us, it does do a little bit of work. I mean, if we become unconscious, we don't remain standing, we collapse, right? Yeah.
What about like a goat when you scare it, it goes stiff?
Yeah, I don't know.
That's so cool though.
Yeah, I'm not sure what
Venezuela goats.
causes that. Yeah.
That has to do with the numbers and hormone that they send out through their blood, and it causes their contractions.
Yeah.
That's a good evolutionary trait they got there.
Yeah.
Just freeze up.
Yeah.
Goats can hop around when they're frozen.
So let's do a little calculation here then. It's not a big deal to calculate work. Let's look at something like this example. So let's take the lawnmower guy here. He's going to want to calculate how much work he's doing if he exerts a constant force of 75 newtons at an angle of 35 degrees below the horizontal. So that's just theta, right? So how much work is he doing as he pushes the mower 25 meters on level ground? What would we do? We're just plugging stuff in. What are we plugging in here? What's the force going to be? Sarah? 75. Okay, so when we plug in values here for this stuff, we're going to get work equals 75 newtons. My displacement or his displacement is 25 meters. And we're taking the cosine of what angle?
35.
Okay, throw it in your calculator. What do we get?
What are the units?
Okay, we'll get to that. Yeah.
Oh,
So what's the numerical part? I guess that's 75 point.
1,535.9.
Okay, 1,000, say it again, 1,000.
1,535.9.
0.9. Okay, and we can only keep how many sig figs here? Looks like 2 with the angle, right? So
Yeah.
1,500.
Yeah.
And the units look like newtons times meters, right? The cosine of 35 is units, right? So Newton meters, and that's correct, but Newton meters are important, right? Just like we gave units of force their own unit because they're so useful. Well, we're giving units of work their own unit because they're also useful. So we call a Newton meter a joule, and we denote that with a capital J. So it's the joule. Have you heard the term joule before? You've probably heard that in chemistry, I bet. What is a joule also a unit of? What was that when you guys were doing, you were talking about joules. Probably it was when you were studying, maybe it was when you were studying some thermo stuff, some heat, right? And you converted maybe joules to kilocalories. Okay, so that's a unit of what then?
Heat.
Heat, okay, heat's fine, heat, energy, right? And so it's a unit of energy. So joule is a unit of work slash energy. The fact that they use the same units ought to lead you probably to think that they're pretty strongly related. Right? And they are. Okay, let's look at this example. This poor sap is having to push that crate up that ramp. So what's he got going here? He's
Look at the hole.
what can you tell me? It's moving at constant speed up the ramp. Okay. So what do we got to do here? Think about this one. We're going to figure out how much work he's doing on the crate. What do you think? What's our definition of work? Okay. So if we're calculating, first time here, we're going to calculate, okay, the work he does on the crate. So what force would we necessarily need to be talking about that?
500 newtons.
Yeah, and then how describe that? That's the force.
That you exert
Good, that the man
On the-
exerts
crate parallel to the ramp.
on the crate, right? Does that make sense? So the force we're talking about here, if we're talking about, we have to be specific here, we're talking about the work that the man does on the crate, then we have to use the force he applies to the crate. Okay, make sense? Okay, so that's equal to 500 newtons. Through what distance does it push it? 4 meters, okay. And what's the angle here between the force and the displacement vectors? It's 0, isn't it? Yeah, he's pushing this in the same direction that it's sliding. Agreed? You guys see that? Okay. And then, I don't really even need to write this, but what's the cosine of 0? 1. Okay. So the most work is done when the force lines up with the displacement, right? Okay. So we end up then with, that's easy, what do we get? 2,000 joules of work he does on the crate. Okay. How much work does he do on his own body? Because he's moving with the
So
crate,
we're
isn't he?
saying that he's moving in the same direction as the crate.
Okay, he's moving in the same direction as the crate. Is he pushing? What about that one? His displacement is also 4 meters then, right? Agreed? Okay, so how much work is he doing on his body? You know, that's a little bit hokey in a way.
How are we supposed to find the?
You can't really do, I mean, it's,
Are you supposed to calculate the normal force and then drop that?
okay, so what might be a good way to consolidate the forces and look at their interactions?
Well, you know he's 85 kilograms, so that you can find out the
Right.
normal force and then.
How do we usually, if we want to see how the forces are interacting, what do we do when we got a bunch of forces going on?
Free body diagram.
Free body diagram, okay, good. So what are the forces now? Let's look at the forces acting on this guy, right? Because now we're talking about the work being done on the guy. And this, you know, I would object to the way this question is stated. And you'll see why. So what are the forces acting on this guy?
Gravity.
Okay, gravity's pushing down.
Normal force is pushing up.
Normal force is pushing up, and so if he's going up the ramp, I guess that's pushing at an angle, right?
And then
What else?
body
So
push, push going.
crate is
from the
exerting
crate.
force on
The crate is exerting force on it. Yeah, the crate's exerting force in which direction?
parallel to the.
Right. Okay, so it's exerting force like so.
And then he's exerting force on the crate.
Now, what's the magnitude of the force acting on the guy due to the crate?
500 newtons.
Yeah, it's gotta be. Defend that answer, how come?
And what?
Constant speed, isn't it?
Constant speed, okay. But
That's how much
now
force
think
he's
about
exerting
this.
on the
Action,
Man,
reaction, pair.
okay, good. Man pushes on crate,
crate. Pushes back.
crate pushes on man. That's a single force, isn't it? That's one force shared by two bodies. That's an action-reaction pair, right? So really, we're describing the same force when we talk about this action-reaction pair. That's just gonna be F, right? And then, what else is going on? How is he able,
Pushing himself.
he pushes on the ground, doesn't he, right? He's pushing on the ground, and the ground is pushing back on him. Make sense? Okay. So, in what direction is he, I guess he's pushing on the, assume he's walking up the ramp. So he's pushing on the ground, put you backwards, right? And there's an action-reaction pair there also. Man pushes on, we'll say ramp for ground. Man pushes on ramp, ramp pushes on man, right? In what direction is the ramp pushing on the man? Yeah, it's gotta be going to the right, doesn't it? Everybody agree? Okay, and so we're gonna have, those are the forces acting on the guy. He's moving, how is he accelerating?
Forward, and upward.
Forward and upward, but doesn't it say on here somewhere that it's moving up at constant speed?
Oh.
So is there any is there a net acceleration on the guy? So what must all those forces add to? They'd all have to add to 0, right? So if we wanted to calculate the force he does on himself, that's kind of a dumb question, right? Because he doesn't do work on himself. What are things that do work on the guy?
The crate.
The crate does, yeah. The ground, right, or the ramp. Okay, let me ask you this. How much work is done on the man due to the crate?
500
How much work is done?
Negative 2,000.
That's exactly it, negative 2,000 joules. That's exactly it. How come? Look at our definition of work. The force acting due to the crate is 500 newtons, right? What's the displacement? 4 meters. But what's the angle between the direction of the force acting on the person due to the crate and the displacement? Right? The crate is pushing on the person.
It's 180 degrees.
It's 180 degrees, right? Because he is being displaced up the ramp with the crate, right? So we're going to take cosine of 180
Which is
degrees,
negative
which is
1.
what?
-1.
Negative 1, and so we get back an answer of negative 2,000 joules, right? So if we want to talk about the work being done on the guy, we have to talk about the work being done on the guy due to a specific force, maybe, right? You can't do work on yourself. If you could, I could just grab myself by the shirt collar and just pick myself up in the air. That'd be a pretty good trick, right? Yeah. All right.
Those two.
So, we'll skip this guy. Let's look at this one instead.
Whoa.
No, but he's going up.
Okay, so this time, ski patrol lowers a rescue sled and victim having a total mass of 90 kilograms down a 60-degree slope at constant speed. The coefficient of friction between the sled and the snow is 0.1. How much work is done by friction as the sled moves 30 meters along the hill? So we're gonna make kind of a running tally of the work done by these forces. So real quick, does this make sense? What are the forces acting on
Gravity.
gravity, which they're calling W for weight,
And then the tension in the rope.
tension in the rope,
Friction.
and the friction, okay?
Yeah.
Right. Now, what about normal force? That's a force acting. In what direction is the normal force acting?
Out.
Perpendicular with.
So the normal force is acting at that angle. Is it doing any work? No, because it's perpendicular to the displacement, right? So normal force does no work. Everybody see that? So the red forces are the forces doing work. Let's calculate the work due to each one. Let's calculate the work due to friction. Okay, so what they tell us here, we need a free body diagram, Bill. This is good, this is a good problem, I like this. There's 60, so that's 30 right there, right? So if we make a free body diagram then, we've got mg, right? We've got tension, we've got frictional force, and we've got normal force. Okay, what's going to be the reference frame? You know, what coordinate directions would we choose here? We could do x and y, but if we do x and y, we're going to have to convert lots of forces.
The perpendicular.
Perpendicular and parallel, how about? Okay, so perpendicular and parallel. So let's just say that this is going to be, we'll call that, which way do we want to call the positive parallel direction? Up, okay. So that's going to be parallel, and that's going to be perpendicular, right? And so we'd have to break up the gravity into components, wouldn't we? So we can break this up into a parallel component and a perpendicular component that are at right angles. And this would be a 30-degree angle right there. Would you buy that? Yeah, that's 30 up here. That's 60, so that's 30. Yeah, okay. Like so. So then if we orthogonalize this free body diagram, we're going to get T, F. We're going to get, we'll call this, well, that's going to be mg cosine 30. I'll just call it theta, how about? And then we're going to have mg sine theta, good.
And then the normal force.
And then normal force. Right? So why do we have to do all this stuff? Well, they didn't tell us what the frictional force was, right? So we have to figure out what's the magnitude of the frictional force.
They give us coefficient.
They give us coefficient, but they didn't give us the force, right? So if we come up with equations of motion, this is pretty impressive. You guys can do all this stuff. I like this. We can do some real things here in physics all this stuff. So what's our one equation of motion?
mg cosine theta, or no,
Wait, which one?
t plus f minus mg cosine.
Okay, so if we're going to look at the parallel component, the parallel component of the net force, we're going to get two positive contributors, right, that are pushing in the positive parallel direction. So we get T plus friction minus mg cosine theta equals what?
Isn't it the other way around because he's moving downwards?
He is moving downwards,
So
you're
the
right.
friction is.
So if he's
so
moving
would it-
downwards.
So would it be mg cosine theta minus t plus f?
No, because if he's sliding down the hill, the friction's resisting his motion, pushing up.
Okay.
See what I'm saying?
Yeah.
Okay. So what's the net force?
Ma?
Okay, but specifically,
Zero.
zero, good. Constant speed, so there's no acceleration. So there's one equation of motion, that's a good one, right? And then if we look at the perpendicular component of the net force, what do we got? Positive would be normal force minus mg sine theta equals 0. Good. So there's our other equation of motion. Okay, so we just need to solve for F, don't we? Right? So,
F equals Fm
yeah, so I guess did we even need here, we know what the coefficient is. Oh, we need normal force, don't we?
Yeah.
Right, because we need to know
Friction.
Well, doesn't.
Yeah, they don't tell us what tension is, do they?
They do not.
They do not. Okay, so if I were to,
Is it F of N just equals
Yeah,
mg
one
goes right
minute,
there?
say now.
Or is it?
say it again?
Yeah, 1 minute.
Oh, well, we may not finish. Mondays are too short.
Yeah.
Right, so if we're trying to find what the frictional force is, the frictional force we can get, we could solve for F in terms of stuff up here that we know, right? I mean, in terms of other quantities, but we don't know T yet.
Well,
Right.
F of N, using the nomenclature as F of N equal mg sine theta, and then you just put that in with the coefficient of friction and find it.
Right. Right, okay. So anyway, we'll finish this up tomorrow first thing.
I think we should bring back like the entire schedule. And then back.